Hey everyone, I'm Miro, and today I'm going to talk to you about, wait, no, that's wrong, non-conforming C++. Also, I would also like to call it the committee exposed, because you're going to hear some things today about the C++ committee that are going to fundamentally challenge your assumptions and what you know about them. In 1 hour, you will think a completely different way in who they are and what they are. In fact, you all think that you've come here by your own free will, but no. Here and in St. Petersburg, by the way, Dobry večer, and have been handpicked by me to show up here with a little bit of mind control magic. Because I believe that you, here in Munich and in St. Petersburg, are the programmers with an open mind, so we can receive the truth that you are going to hear today. And if you want to know how I made you come here, just talk to me about chemtrails later. It's no big deal. So shortly after I announced my talk on Twitter, we have already seen the cruel display of the C++ committee in public, giving me thinly veiled death threats. Let me quote here: "Good thing we're a committee and not a mafia. You'd be swimming with the fishies for this tweet." This only lets me believe that they're going to do something else. And to which another committee agent replies, "C++ is what the committee says it is. C++, it's not C++, which I think must be code for something, because I have no idea what this means." Continuing, "And there are unfortunately no fish in Denver," which I don't think is true, but I'm glad that they think it is. So let's dive in. Let's open up the secret box of the committee and see what do compilers do for us that the committee doesn't want you to know about. And we start with a feature called case ranges. So I think many of you have seen switch statements that look something like this. You have lots and lots of cases, and they all do the same thing with one single line of code at the end. A sane programmer would now say, go and say, well, I'm just going to do an else if, because this is a lot easier to read and write. But the good folks behind GCC thought, hey, no, we can make this declarative again and give you case ranges. So you can actually use ... surrounded by white space on both sides. And this is equivalent to the left side. It will generate all the cases. So how does it feel to...
Ever matching for if we have this?
No idea. But also, I forgot to say, please keep your questions to the end. That was a misunderstanding with the organizers. Because you cannot interrupt truth, you just don't. So now that you have seen the first secret of the committee that they are keeping from us, let's go to the next. Unamed structure and union fields. And in fact, this one is so ubiquitous. It has leaked so much that people think it is actually part of the language, but it is not. Any of you familiar with graphics programming and seen 3D engine code or physics code have seen a structure like this, where you have a structure with a union inside, and this union has a float array and also a structure, and this structure has members. And note that neither the union nor the structure has actually a type name. One of these is not like the other, because one of them is part of C++ and the other is not. And the answer is that the union is okay, the struct is not. We can actually simplify this a little bit and just make the whole thing a union, because with C++ 11, the committee finally declassified unrestricted unions, and we can just have any kind of special member functions as with any other struct. So the idea here is that you can use either the member names of X and Y or the array access, and they occupy the same space. This lets you write to X and to Y, and then read from the array at index 0 and 1, and you get the respective values. It also allows you to use a dynamic runtime index to access your fields. And we already heard about OpenGL today, and many APIs like it have functions that take a float array to transmit data to the GPU, and this way we can turn our array into a float array, our structure into a float array. Now you're thinking, well, this is C++, why don't you just overload the subscript operator? And I tried. The compiler didn't like it. It generated terrible code, so just don't. Another useful feature that you find in GLSL, which is the shading language of OpenGL, is that it's often convenient to interchange between positions and colors. It is a very useful thing to do. And with a setup like this, you can actually have two names for the same thing. So here in this case, we modify X, then we modify R, but that has also modified X because they're just two different names for the same thing. And so if you're a company that at this point, you're probably gonna hire some C++ experts consult you, they will have some generic names like Scott or Jason or Kate. But it doesn't matter because they're just mouthpieces for the committee. And they're going to come to you and say, this is undefined behavior, you can't do that. Oh no. Now you're going to panic because they use the U word and the B word, and it means your code is broken. But no. Stand there, be vigilant, stare at them. And then stare a bit more, stare more, and say, so what? It runs on tens of millions of games. It works on our machines. And then if you declare your victory and they leave, which is one victory for this plus rebellion. So we are done with this feature. And the next one is a convoluted name, Conditionals with omitted operands. Now imagine you're developing some kind of configuration reading system, and a value in the configuration may not be present, and if it is not, you just create a default value. So at the top we have our read function that in this case creates a unique pointer of something, but it could be an optional, it could be a shared pointer, it does not matter. And the default value function, as the name suggests, just does that. So we combine them in this neat little utility, and this should tingle something in your brain and say, this should be a conditional operator. This is easy enough for it, right? So you're gonna try, and then you realize that was not a good idea. Because now you run the possibility that you call read twice. If the first call to read returns a null pointer, then it's gonna read again. And if read has side effects, like for example, advancing a file pointer, well, you just broke in your configuration system. So of course, we have to hoist this read out of the conditional, which is ugly, but it's still shorter than the other solution. So let us remind ourselves, how does the conditional operator look like, right? We have some kind of Boolean condition on the left, followed by a question mark, by some other expression, followed a colon, and yet another expression. The two expressions on the right side need to have a compatible type, so something where they both can be converted to. Now, the find folks by GCC, once again, weird, thought, hey, why don't we simplify this? And so they introduced this version that you can omit the middle expression. And it's the equivalent as if you have repeated the left expression and put it in the middle, with the difference that it is evaluated only once. And this now lets us write what we wanted to do, right? So this is also, again, the premise that both operations or both expressions need to have a compatible type. So the left expression does not actually create a Boolean, right? Because you would think that's what the test needs. But no, the read, the expression is evaluated on its own and it sets its own type, in this case a unique pointer. And only then is it trying to convert it to a Boolean. So we end up with two unique pointer expressions, and they're fine. So works. If you go online, you will find that many people have started calling this the Elvis operator. For some weird reason, and also in other languages. I mean, once you see it, it's obvious, right? You should just look at it, right? You stare a bit, you like tilt your head a bit, and then you see it. Do you see it? I see it. I mean, once you've seen it, it's so obvious. You just can't unsee it. So continuing with our box of treasures, designated initializers. This one is very useful. You have a structure with public fields. And usually we'll use aggregate initialization to create an object like this. Designated initializers let us use the name of the field to initialize each value. This is very useful because it lets us mimic something called name parameters. So imagine we have a function to open a file and it takes one of those parameters objects. You can actually create one directly inline in the core. And this now looks as if your function had named parameters, which is a lot easier to read than this because true what? False what? You don't see. You have to go to the definition to understand what true and false mean. So the good news is that this has been declassified. We can actually use it in C++20. So I won't go into more detail in this because other people will have more to tell. But because the committee hates you, they decided they won't go the full mile and they will still keep something in designated array initializers. This is again a setup that I've seen in many code bases where you have some enumeration, in this case colors, and associated arrays, I would call these. Arrays that have additional information for each enumeration, and you access them as down here. with the enumerator as index into the array, and you get the associated value out. Now, if you're like me, and you really hate lists that are not alphabetically sorted, you're gonna go and do this, right? And now you broke everything. Because even though I didn't actually care about the numbers, that's why I didn't write them down, the numbers were important. And so now here green, yeah, no, nothing green, you get what? Black, I think, and here you don't get the code for white, no, you get the code for yellow. So system completely broken, of course the obvious solution is to add those numbers. But then again, I have to maintain those numbers. I don't care about them, they're just a crutch. But it does work. If I sort the array, it still works. But now if I want to add a new value, I have to search for the biggest one. So the friendly people behind GCC thought, hey, you can do better. And give us array initializers. So you can actually put the index in the brackets, and the compiler will make sure that the values end up in the correct order inside the array. And this solves all our problems. If the order of the enumeration changes, doesn't matter. You can fill those arrays in any order you want. It doesn't matter. The compiler will make sure that it's all in the right order. The syntax for this is very simple. You just have these bracket indices, and if any value that's missing is set to 0. If you have a value, like here, that follows one of the designated ones, it just is the next index. So 24 is the index 3. And you can even deduce the size of the array. It's just the biggest index determines the size. And of course, the order, as I already said, doesn't matter. So this array naturally has size 7, because the 11 here has index 6, because it comes after the 5. But wait, there's more. So we all know how to create an array of zeros. It's like the most easiest thing you can do in any language. You just use the value initialization. But what if I want an array of 12 ones? Well, I have to write it out. And of course, screw up because this one is missing. So the last one is 0. Now, have fun finding that bug. So we can actually combine this with something we've seen before and use syntax that we're familiar with and use ranges for this initialization. And of course, we don't need the size because it can be deduced from the biggest index. And we can combine these however we want. The only restrictions here that these must be constant expressions, so f must be constant for x, compile time constant. The result of f is index 3, and the value 100 on this result index 21. So this whole array has 22 size. Speaking of arrays, flexible array member. So this one is going to be interesting to explain. There are systems where often you create a certain set of data, and the size of the data doesn't change. But you want this data to be as quickly accessible as possible, with as few pointer interactions as possible. For example, many virtual machines like Java, .NET, or Lua, Python, they have immutable strings. Once a string is created, it cannot be changed. So they also have a hash table of these strings, which makes comparison very quick. It's just not even a hash table lookup, it's just a pointer comparison. And the hash table is only there to prevent duplicates. So I would like something like a shared pointer of vectors. So they're also reference counted, a garbage collector, pick your poison, and generalized to any kind of T. The memory layout of this is going to be something like this, right? Each block is a separate allocation. The shared pointer, you don't really care, it's somewhere on the stack probably. So we already know that we can use make share to fuse these two allocations together. But what I really want is this. I want everything in one allocation, and I don't want this indirection either. I want to be able to take the pointer to this thing, add an offset, and reach the data. Only one indirection. There are a few options that we can try. My boost is full of nice little gifties. So let's try static vector. If you don't know static vector, it takes a compile time constant here that represents a static buffer. It's a fixed capacity that is allocated inside the object that you can fill up to n. So this does has the advantage that we don't have any extra interaction. Once we know where the static vector is, we know where its data is. However, the fixed capacity is a problem. If I have less than n elements, I'm wasting memory. If I have more than elements, well, I'm shit out of luck, because it can't hold more. So there is one that can, though. It's small vector. It's similar principle, but if you try to put more in than it has a capacity for, it's just going to turn into a normal vector, which means an extra direction. So we're back to square one, and we're also wasting all this memory. Because this buffer is not used, the vectors will be contiguous, you cannot split the data into. So, again, nothing used. What do we have to do? Well, of course, you do it yourself. So, imagine this view of memory. On the left is the start of our thing, right, where the memory of our object starts, and it just goes off to the right. And we have some kind of header structure. This is the thing I'm going to interact with. It knows the size, it can give me iterators and things like that. And the layout in memory I want is that this thing is at the front. And the data is just arranged after it in memory. The first thing we need to do for this is to determine how many bytes do we need, which is very easy. We just take the size of the header and enough size to store in doubles, which in this case, that's my data. Yeah, okay, then buffer. Okay, we construct this thing in there. Okay, we construct the doubles. Fine, cool. Then we have to do a bit of reinterpret casting, but that is safe because there are actually doubles there, so you can do this cast. And then we just do some arithmetic on it. Now, when you run this code, two things can happen. One, it just works. Two, it crashes with righteous fury because you dare to have unaligned loads and stores. Right, so if you're on an ARM device, this is your future. If you're on an x86 and the compiler hits you, then it generated aligned loads and stores, which also crash your program. So unfortunately, alignment is a thing that we have to care about. So we have to figure out how much space do we need after our structure to start in doubles, because the double has to start on a memory address that is a multiple of 8. At least that's the assumption I'm making for this hypothetical machine that crashes a lot. So I just call this an X, right? And we're going to figure out what is this X. It looks like it's just the size of a double. It is already 8 bytes. It has an alignment of 8 bytes, so we just add 8 bytes. But really what we want is the alignment. That's the thing that matters. And this kind of works until you put more stuff in your header. And suddenly the header is more than 8 bytes big. So now you can do this because you're just going to override part of your header with the doubles. So let's figure this out. We know we need size for a header. Okay. Then we need the alignment of double. But then we subtract 1, right? And then you one. And then what? Okay, I promise you this is not a mistake. If you've never seen this pattern, this is how you round up an integer division, because integers usually round down to 0, and this only works for positive numbers. But this gives us the number we want. So we take the size of the header, we divide it by the alignment, round it up, and then times the size of a double and the alignment, and that's the real distance we need. So we just plug this all in our system that we had before. We can make this construction because it only depends on compile time values. We replace here the size with an X, the offset with the X, it's just X everywhere. Down here we see another reinterpret cast because we actually have to turn the pointer to a header into a byte pointer first, so we then can add n bytes to it. Otherwise we would add multiples of a header size. Okay. However, this only works if your buffer is already aligned 9 bytes at least, right? If the start of your buffer is a multiple of 4 and you add 8 to that, you're still not at a multiple of 8, so it's going to crash again. So if you use operator new, like here, you're most likely not going to run into this problem because it has to return an address that is suitably aligned for almost anything. Caveats apply. But if you're doing your own memory management with your own allocators, then you have to think about this. But that's your job, not mine. There's one help we can use. We can tell this header structure it has to be aligned just like a double. And that helps because the compiler will make sure that when it is constructed somewhere, it's actually going to be hopefully on an 8-byte boundary. However, things are never the way they seem. This line, ladies and gentlemen, this line, it's a massive, massive troll. This line it makes you insane. Because sometimes it works, sometimes it doesn't, sometimes it crashes, sometimes it doesn't, sometimes it gives you the right result, sometimes it doesn't, sometimes it corrupts your memory, sometimes it doesn't. And then you get raging mad at yourself because you think, but am I too stupid to understand this one simple line? It's obvious what it does, isn't it? And then you get mad at the compiler thinking it's broken. But no, it's doing what it's supposed to do. And then you just, why C++? Why are you doing this to me? I thought we were friends. No. Then you just get sad. Oh, well, there is no gold at the end of the rainbow. Oh, the pot is full of crap, and you can get rid of it. Because this is why the committee hates. So let's have a look at working graph, comma, standard for programming language C++. Section expr.new, paragraph 19. There's also a link as evidence if you want to verify. So we look at this quite lengthy paragraph and we find this thing, which explains how the placement new operator for arrays translates into an allocation function. Because, which is also called new because that makes sense and we need more ambiguity in the language. So don't be confused by this 2f, right? It's only there to demonstrate that it is appended to the end of this function call. And we've been using this the whole time, right? We use it in this form, they give it the pointer, and it just added to the end. But wait a second. What is this? What is this x here? Where does it come from? I didn't write it. What is that? And so you keep reading the standard and continue down, and then let me read to you this horror story. Here, each instance of x is a non-negative, unspecified value representing array allocation overhead. The result of the new expression will be offset by this amount from the value returned by operator new. This overhead may be applied in all array new expressions, including those referencing the library function operator new, which is the one we're using, and other placement functions. Oh, well, the amount of overhead may vary from one invocation of new to another. What the? Okay, let me summarize. Non-negative, unspecified overhead in all array new expressions and placement, and the overhead may vary from one call to the other. And this reason is why it is literally impossible in C++ to create a buffer that is guaranteed to be big enough for the result of a placement new array expression. You cannot query this X in advance. It is unspecified. It can change with types and addresses and anything. You just cannot do this. And so if there's one thing you take from this talk, never, ever, ever use the array form placement new because you cannot guarantee that it works. It is a source for stack corruption, for heap corruption. Just don't. If you're using it right now, rip it out. Replace it with some kind of wrapper that checks the size of your buffer. And if at this point this is going through your head, well, congratulations, you're a sane human being. Because the committee really thrives on ultimate despair. So can we somehow salvage this? We know that this is the problematic line here. Fingers. So luckily, we do have something in C+17, which are the uninitialized algorithms. They deal with raw memory, and they can create objects for us. And they actually do exactly what it sounds like they do. There's no added overhead or anything. So this really goes ahead and just creates one double after the other in memory. The rest doesn't change, but the traps never end. Because now this entire expression on here is also undefined behavior. Who knew? Turns out we don't actually have an array. Just because you create multiple objects in order, in memory, does not mean you have an array object. And this is just, the committee is just, they just want to see you suffer, really. This data pointer points to an array of one object, the first. Data 0 is the index of that object. Data 1 is the past the end iterator for that object. And data 2 is just undefined. So you cannot technically use this, and this is technically the reason why it is still today impossible to implement standard vector in C++. Standard vector is magic. And there are other reasons why it's magic. So, what do you do? As far as I know, there's no standard C++ way to implement this in this efficient way that I would like it to have. Which means let's just throw the standard out the window and make our own rules. So the good people behind UCC thought, hey, let's add this. It's an empty array at the end of a structure. If you're using Clang, you may have to make it a 0 size because of reasons. It's weird, but it's the same thing. What this now does is it instructs the compiler to manipulate the size and the alignment of the structure so that when you construct it, you can have the array right behind it. It's almost as if it was created for this purpose, isn't it? Now we can actually do what we initially wanted to do. We just take the size of the header and we add numbers to it, and that's it. That's the size. We create the buffer and we create the header. And now the compiler is taking care of the padding necessary. This is the dark area. The integer is the first 4 bytes. And we just construct our doubles over there. And we use this data member, which is actually not really a member of the structure, it's just symbolic. It doesn't exist in the structure. If you take the size, if it was ints, and you take the size of this header, it would still be 4. There's no hidden pointer or anything. It's just a offset calculation that the compiler does behind the scenes. We can then, of course, use arrays, because we are accessing an array. The compiler doesn't care how many elements it has, it is using an array to access array elements, even though we constructed them individually. And then, of course, don't forget to clean up after yourself. We have to, because we constructed everything manually, we have to destroy it manually. But we can do that in the destructor. We could also do the initialization in the constructor, but that's an exercise for you. So, we took a lot of explaining why you can do something just to show you this tiny little feature, didn't it? But it just shows that sometimes you have to jump through hoops to achieve something that could be really easy, if only the committee allowed it. So, we're done with arrays, almost. The last trick here is labels as values. For this little exercise, I've created something like an interpreted bytecode language. It is very simple, it only has these 2 instructions. There are no operands or anything, you just all do predefined arithmetic operations with a constant. And you can write a very simple interpreter for this, which is just an infinite loop running over a switch instruction. It just keeps fetching the next instruction and goes to the case that is represented by this instruction. We see here, they just do this built-in arithmetic operation on the value, and if you reach the whole code, you are done and return the value. I don't think this is anything ground-shaking, and I wrote a little benchmark for this. So it's really just for reference. What I'm doing is I'm creating a sequence of uniformly distributed instructions, excluding the hold, because I want the benchmark to actually run all the way to the end, so I then insert a hold at the end. And we get some benchmark numbers out of this. So if you've never seen the output of Google Benchmark, you have here the name of the benchmark. This is the problem size, so in this case, this is just how many instructions am I generating. The time here, this is the total wall time, so how long did it take from the start of the process to the end of the process. And this is called the CPU time, which is trying to filter out some of the things that aren't relevant to the computation itself, like context switches or waiting for page faults and things like that. So what if I told you that I can make this very simple, trivial switch loop run in about 13% less time by doing things to it, volatile thing. This is what I did, and you can already see that it's related to goto. The numbers here, except for the first one, which is really a real outlier, we have on average about a 13% less execution time. So goto. This is a for loop. You see it? Obvious, isn't it? I don't think I need to explain gotos. I mean, it's like the one thing that everyone hates. So GCC, again, has this thing where you can take the address of a label and store it in a variable. And this empowers us, because this is the first time ever in C++ history that you can program indirect jumps. This is, until now, only an explicit privilege of the compiler. We have indirect calls with function pointers. This gives us indirect jumps. And yes, you can shoot yourself in not just foot, but pretty much everywhere, nuke yourself to orbit. But of course, we're adults. We are responsible. And the next thing we can do with this is put it in an array. And then use a value determined at runtime to jump to. So we can very efficiently build our own jump table. For good measure, we can make the table const expert just because we can. And it's C++, right? This is all just C until now, if that's something. So now we're gonna do very volatile things to the run function from before. In fact, we're gonna just remove it and replace it completely with our own jump table using a feature seen before, which is the array initializer, just to make sure that I don't screw up the assignment between the index and the label. Then we have our labels, right? Just do the actual computation. And then we have this, which is also the same as in the switch. We just read the next instruction, and then we use that as the index in our jump table. We have the remaining labels, and we have one goto at the start of the function to determine which is the first instruction to jump to. So this is the how. Now let's look at the why. Why is it faster? And for that, we're going to look at some assembly. It is very cleaned up and tidy assembly because it's a lot and otherwise. But we see the structure of the switch, right? We have here this jump that does something based on a register value. RAX, that's a register of the CPU. So it's using the value of the register as an index into a jump table. And this jump now can go to the switches cases. So we have the labels for the A1, the A2, and so on. So every case has generated a label on the CPU, the assembly. And these arrows are red because this is a indirect jump, right? Indirect jump instructions are very expensive for the CPU because it cannot usually predict where it goes. So it may have to stall or wait or flush pipelines and do all kinds of dirty things until it can continue execution. Then we have these other jumps here that are just static jumps, predictable. They don't slow down anything, and they just go back up to the switch to repeat the loop. This is the break, basically. Let's compare that to the goto solution, which has a lot more code. It's about 20% more code than the switch. But we see that this block just keeps repeating and repeating and repeating. And in fact, the only difference is this first line, which is the arithmetic instruction that is encoded here, right? We see the addition, the division, and then it's using some form of weird addressing to get the constant, right? The 1, the 3, the 7, and so on. But then the rest of this block is character for character identical each time. In fact, it is pretty much identical to the jump that the compiler generates for the switch, except it generated a jump table, whereas we created our own. So the compiler really had the right idea. It recognized that the switch cases go from 0 to n and just created a jump table. But that doesn't really explain why it's fast. The reason for this are these jumps. So every goto is again translated into this indirect jump. And where they can they jump to? Well, everywhere. And I hope this is a head scratcher because I just told you that indirect jumps are bad. But now there's a ton of them. But why is it still faster? And that has to do with branch prediction, or jump prediction in this case. You see, the CPU is trying very hard to predict where an indirect jump is going to land. And for that, we can simplify this algorithm as looking at the address of the jump instruction and a little list of history where this jump instruction went to in the past. And then we just pick one that we think is the most likely to happen again. In the switch case, every single bytecode goes to the same jump. And because our input is random, this jump is unpredictable. Whereas in the other case, every single bytecode has its own prediction and its own entry in the jump tables, prediction tables. And so here, the CPU is analyzing the most likely instruction following after an instruction. And so if none of this meant anything to you, this is the part where you should pay attention. The CPU has recognized patterns in our random input, right? It has figured out that certain instructions are more likely to be followed by other certain instructions. And that's where the speed up happens. If you had truly random input, then the speed up wouldn't be there. It would be the same performance for both, because each bytecode still goes through one indirect jump. And now you're thinking, well, okay, so it works on this toy example, right? This is some made-up, trivial example of a instruction set. But that's not the case. And to demonstrate, I will use an actual real-world application. I chose Lua for this, which is a widespread scripting language that is embedded in a lot of applications. And it is written in C, and its creators had the foresight to actually use macros for their switch loop to modify the switch header, the loop header, the cases, and the breaks, so it can change how this behaves. And that's what I did. So I changed those macros so that instead of a switch in a loop, you have now these jumps between these cases. And then there's a popular benchmark called CMark or SciMark, I don't know, that is used to compare Lua implementations against each other. So these are some values that I ran from the switch version. The numbers represent on average the megaflops per second as this benchmark ran. Here are the numbers from the goto. So let's see the comparison. And we see that we can get a speed up between 5 to 41%, depending on what we're doing. If the benchmark is very heavy in floating operations, then they're going to dominate, and any speed up in your interpreter won't really help. But here, the Monte Carlo integration up to 41% faster. And on average, we have a 20% speed up. So this is real performance just laying there on the ground because the committee doesn't want us to write efficient code. And it's not just Lua. I mean, the actual Lua doesn't use it. But Ruby does this. Dalvik does this, which is the JVM on Android. And the guys of CPython also did this transformation, and they reported up between 15 and 20% faster execution of the virtual machine. So just think about it, right? You have this very mechanical transformation of your code that yields up to 20% faster for all Python programs, basically. And it sounds like something the compiler should be able to do, doesn't it? So, okay, we've seen all these cool things, but of course I mentioned GCC a lot, right? And you're not all using GCC. So if you want to use these things, can you actually use them? So let's look at the support. I mean, if you're married to Microsoft compiler, you're a bit sparse at the bottom there. But if you're not married to it, just use Pine on Windows. Problem solved. All right. Now for the serious stuff, Mike. I am an administrator on the CP Slack, and the agents of the committee have contacted me there on my turf. And so one of them says, hey, do you see me as the enemy? I mean, duh. So I say, well, you're French, and you're the agent of the committee. Now I said you're French because I know who this is. And so I let them know, so they know that I know that they know. You know? A bit of intimidation on my part. So they say, well, if I were an agent of the committee, I might declare your opinion undefined behavior. And of course, we know that the committee, if it's undefined behavior, it just doesn't exist. It's irrelevant. So I say, well, you probably already have, honestly. And now, this is the part that blew me. This is a real bombshell. They say, allowing me to optimize your existence of it retroactively. So this is a real conversation that happened. I didn't make this up. And just think about the implications of this last sentence. The committee has access to time travel technology. Next time you see a committee member talking to a normal person, and the normal person says, yeah, well, I don't like that the language is like this, and that this is a trap, and couldn't we change this and remove that? What is the number one response you get from them? Well, if we had a time machine, we would go back and change things. Now you know. You know. You have to call them out. So I hope that you are now as enlightened as me, and that you will join me in the rebellion of the free-thinking C++ programmers. I will need all your support because I am going to confront the devils in 2 weeks at CPPCon, and there's a lot of them there. So, just, yeah, I mean, thank you for staying all the way to the end, because I know I've sounded sometimes a bit crazy, but I'm not crazy. So, thanks. The end.
Thank you very much,
So I would say
Miro.
the
Thank
first
you.
question
Yeah.
from here.
I think we can go with questions now. So,
Yes.
like again, Munich and St. Petersburg, you can queue near the microphone.
So I was really more. When you were saying the reinterpret cast that you did in the array example was okay because they were both doubles, I'm pretty sure it's not okay. And it's a bit subtle to see from the current standard why it's not okay. So we're actually collaborating with the C standard to make it very obvious that it's not okay. The problem here is that the cast originates from P, but you're accessing a member of the array Q. So the way that the compiler thinks about this is that this pointer remembers which allocation it came from, right? So if you pass from one allocation into the other, the compiler is actually allowed to realize that these are distinct allocations and thereby declare the whole thing.
Right. So basically, to summarize what you just said, the sky is falling. Really? Yeah. We're too cheerful. I should tone it down a bit. Okay. So I tried to summarize what you said. So because the pointer p comes from a different allocation than the doubles, the compiler is able to track which allocation each pointer came from, and it knows that these are not part of the same allocation, and therefore this cast may again reach a past the end pointer, which is actually not a valid pointer to a double. So yeah, reinterpret cast is always dangerous. You have to be very careful and know what you're doing, which clearly nobody does. Okay, do we have a question in St. Petersburg?
I think everyone is just shy. St. Petersburg, any questions?
Well, I don't see anyone at the microphone. So let's take Munich again, yes?
You feel into this label and switch case comparisons. It's very interesting.
Yeah.
Did you try any hardware-specific compiler?
I did not try hardware-specific compilers for the labels.
Maybe on an ARM compiler, because I'm pretty sure that there is some compilers which would optimize it for you in the way you did it with the labels.
Right. So I did not try the different platforms. I mean, the speed up is going to depend on your architecture. How good is the branch prediction, and how deep is it? And of course, a normal application, which is something I forgot to mention, a normal application does have random distribution of instructions, right? You have similar instruction streams, a pattern, a function call always starts the same way, it always ends the same way. The setup of parameters before a call always is the same. So there are patterns in normal applications, which also why the Lua benchmark probably went faster, because normal Lua bytecode does have repeatable and discoverable patterns. Okay, next. There was something? Oh, yeah.
Why are the leading agents?
Excuse me?
Why are you the leading agents?
Oh, I know.
But you believed in that reinterpret cast, right?
Because I know that unfortunately he is speaking the truth. It is a rare occurrence, but they are true about the Bible. Like the scripture, they stick with it. If the scripture says it, it's true. And I know that this is what the scripture says.
How should we tackle that?
Oh, wow. Do you have a few hours? Yes.
What about using the goto things to measure how good is the random algorithm? No? I mean, it's like you could somehow try to put them the other way around.
That is a good idea to use the the goto method to determine the quality of random number generator. Right, so I used the Mersenne twister, and it is known that it has difficulties in its distribution. I didn't try it with others because this was just, I needed something to bench against. Yes?
So you said that the reason that this labeling thing had a speed up is because there are some underlying patterns in the axis, and the previous implementation couldn't handle it because it basically has just one indirect jump.
Yes.
So it acts uniformly, and the other one actually finds that it's not uniform purely.
Yeah, so
Do you think that you can actually compile it with another distribution like Ocean to actually prove that it's because of the distribution?
I mean, I could try, but it would just, I guess, prove the point more because it's less. I mean, the problem is not necessarily distribution; it's also random number generator, right? Because it's the basis for the distribution.
But I mean, like this, it wasn't obvious to me that it's this. The problem is this: it's not a pure distribution there. So
I mean,
if you can like somehow show that it's actually that this is the thing.
Okay. So right. So you would like to see that the data isn't really random.
I would like to see that there are actually these patterns to be found.
Okay. Yeah. I mean that's good. If you know how to detect these patterns, I mean I'm just trusting the
So one
CPU.
idea would be to try different distributions, not just the uniform, but some other, because basically for like Ocean you would have definitely a pattern there, right? And since in the switch you have just one indirect jump, it will not be able to run it. But the other version should with many indirect jumps.
Right. So to summarize, you think using a different distribution will give insights into the randomness and the predictability of the data, or how it applies to the different usage of the jump instruction and the transportation.
To support your point.
Oh,
If you could support your point.
okay, yeah.
Because it's not like we know the answer rate. There is no Bible for it.
Right. Okay. Yeah, I understand. Okay. Thanks for the suggestion. Any more? No? St. Petersburg? No questions?
I think now from us. Actually,
All right,
good luck
yes,
with this
that's it.
talk at
Thank you all for your
CPPCon.
attention.
Yeah, thank you.